Hello everyone and welcome to this week's lecture. So last week we discussed recurrent neural networks and we saw the different approaches to deal with time series problems or data that comes in a sequential format. Today we're going to talk about some special network architectures including GAN and different other architectures that can speed up the learning and help us find a model that performs reasonably well on an unseen test set without spending too much time waiting for it. So let's start by refreshing the concept of unsupervised learning and transfer learning, because these are core to these modified architecture and training approaches. So the deep learning systems we've discussed so far are based on supervised learning. Essentially, they require that each training example to be labeled with a value for the target function. Now, that value could be a continuous value if you're developing a model to make predictions, or it could be a label if you're developing a classification model. And although such systems can reach a high level of accuracy on an unseen test set, they often require far more labeled data than a human would for the same task. For example, a child will only need to see one picture of an animal rather than thousands in order to be able to recognize that animal in new pictures or different settings. So our network, however, requires thousands of images with the same animal in them in order for the network to learn to identify that specific animal in new pictures. So clearly something is missing in our approach to deep learning. So it is one of the possible problems is that our current approach to supervised deep learning makes some tasks totally impossible just because the requirements for labeled data would exceed what the human race can essentially supply. Okay, so that would be a big problem here if you run out of training data, of labeled data essentially. I mean, that would mean that we would have to stop essentially developing new, more complicated models just because we don't have enough training data, labeled training data to train these models. And and even if we had enough data, unlabeled data, and we would just need to label it, that would require so much time and it would cost so much money to be able to label all that data. So for these reasons, to reduce the dependence on labeled data, we try to look at learning in a different way through what's called unsupervised learning, transfer learning, and what's called semi-supervised learning. So unsupervised learning algorithms essentially learn from unlabeled data, input X, which we have a lot of them, obviously. And unsupervised learning algorithm, the outcome of these algorithms is typically what we call a generative model, like LLMs and other models that you've heard of probably with artificial intelligence. So essentially what these models are not trained on labeled data, they're trained on huge sets of unlabeled data. And they can still produce realistic text, images, and audio and video similar to what they learned, rather than simply predicting the labels for such data. Transfer learning algorithms, on the other hand, require some labeled data example, but are able to improve their performance further by studying labeled examples for different tasks. So essentially, it makes the need for labeled data less. So the idea here is that if we trained a neural network to recognize a monkey, we used a lot of data to recognize the monkey in images, then maybe if we have a new task to recognize a dog, maybe we can use that network that was trained to recognize the monkey and just supply it with few examples of images with dogs in them, and then the network would fine-tune the weights to perform the new task, which is identifying dogs. So that's the idea of transfer learning, and as you can imagine, that leads us to require much fewer data than if we had to start training a new network to recognize dogs in images from scratch. We'd have to start from zero, essentially. That would take a huge amount of images. Every time we had to recognize something new, we would have to supply a huge amount of labeled data. Using transfer learning, we reduce the time needed for training and also the amount of labeled data needed. Now, semi-supervised learning algorithms require some labeled data, but are able to improve their performance further by also studying unlabeled examples. So essentially, in this lecture today, we're going to cover these learning approaches: unsupervised learning, semi-supervised learning, and transfer learning. And you just have to know that these are very important now and becoming more and more important, because the goal of most artificial intelligence systems now is not really to label examples, but to generate, right? Like a generative model, generating answers to questions, generating code, and so on. So let's start with unsupervised learning. So like we said earlier, supervised learning algorithms essentially have all the same goal, which is given a training set of input X and corresponding output Y equal f of X. Learn the function H that approximates the unknown function F reasonably enough. Okay, and we talked about how we have to limit the hypothesis space for H in order for us to learn fast enough and to avoid overfitting the data and so on. Now, unsupervised learning algorithms, on the other hand, take a training set of unlabeled example X, and then the first thing it tries to do is to learn new representations. Okay, so for example, new features of images that make it easier to identify the objects in an image. The second thing is that it tries to learn a generative model, okay, which is essentially a probability distribution from which we can generate new samples. Okay, so two things. First, to learn new representation. This is very similar to principal component analysis or any other method you might have seen in mathematics or physics or any other class, where you try to take data from one space and then project it into another space in order to identify some hidden pattern when the data is in that new space. So that's essentially learning new representation. So the network is trying to project the training data into a new space, a new set of features other than the input features you used, in order to try to identify specific features in the image. The second idea is, in order to generate, what we do essentially is to generate a lot of possibilities and assign each possibility a probability. And then the one we're going to select is the one with the highest probability. So for example, when you're using any generative model, ChatGPT or perplexity or anything else. What they're doing essentially is given your text, they're trying to find what's the highest word that comes next and the highest probability word that comes next and then the next one and so on. So it's all essentially sampling from a probability distribution over the possible outcomes. So that's what we call the generative model. So suppose we learn a joint model, for example, P sub W of X and Z, where Z is a set of variables that are unobserved. And these variables, Z, they represent the content of the data X, which we know, the input X, in some way. So the model then is free to learn to associate Z with X any way it likes. So essentially it's trying to find its own mapping to go from the X space to the Z space. Okay, we don't force it to use a specific map. For example, a model trained on images of handwritten digits might choose to use one direction in the Z space to represent the thickness of pen strokes. So remember that these handwritten digits are represented by vectors of pixels, and each value represents the darkness of the pixel, let's say black and white images. Then the model might then transfer this feature into a new space Z, where one of the components of the new Z vector represents the thickness of the pen strokes. Another might represent the ink color, if we're not using black and white. Another might represent the background color, and so on. Let's say, for example, we're training on images of faces. The algorithm might choose one component of that Z vector to represent the gender, another one to capture the presence or absence of glasses, and so on. Okay, so you can think of it as this is how would a generative model learn different directions in the Z space to represent different aspects of faces. So once we have them in the Z space, we can actually perform operations in that Z space. So all these images here on the right are generated from the learned model and show what happens when we decode different points in the Z space. So we start with the coordinates of the concept for a man with glasses. So this has a Z vector representation, and subtract the concept of a man. So this is the man as learned by our model, and then add a woman, and then you can see that the images generated should represent women with glasses. Okay, so this is how the unsupervised learning then will work, is that we move from the X space into the Z space, and then the network is free to pick whatever each component of Z represents essentially. Now that learned probability model, PW of X and Z, achieves both representation learning and generative modeling, because then if I want to generate the most likely image out of these, if I want to get the most likely image, all I have to do is to integrate out over Z and get the probability, the highest probability image. Okay, and that would give me the output in that case. Now let's apply this concept then of mapping in our first approach here, which is probabilistic principal component analysis.